From here to the stars, I am your host, Stephen Euin Cobb. Our guest today is Dr. Kevin R. Grazier. Dr. Grazier is a planetary scientist, author, and science advisor for a number of popular TV shows and films. My guest today is Dr. Kevin R. Grazier, a planetary scientist, author, and science advisor for TV shows and films. Thank you, Doctor, for taking the time.
It's a pleasure.
You have had a wide range of experiences in space exploration. Most exciting to me was that you were involved with the Cassini-Huygens mission to explore Saturn and Titan. So let me start there. Specifically, the Huygens probe that landed on Titan. You had the dual roles of science planning engineer and investigation scientist for the imaging science subsystem, the visible light camera aboard the probe. Would you describe the Huygens lander in general, and also what other instruments were carried to the surface of Titan?
So let me delineate. The ISS instrument was the main camera, the visible light camera aboard the Cassini spacecraft. It was not the imager aboard Huygens. So Huygens had its own separate imaging system, and what Huygens did was it took data related to Cassini, and Cassini turned around and relayed it home. But in addition to that, Huygens was primarily an atmospheric probe. So most of its measurements it did while descending, hanging from its parachute. It had a mass spectrometer, which is used to take a sample and analyze the composition. Had an imager, and it had an instrument to measure the composition of aerosols, and it even had a surface science package where it fired a penetrator into the soil, or not soil, the surface of Titan, and then it sampled what came out from that little mini impact.
Okay.
So it was a pretty capable little probe for its size. It wasn't that huge.
I was not aware that it drove an object into the surface. The surface was rocky. There were a number of rocks. Did it actually penetrate?
In the outer solar system, a planetary scientist considers ice to be a rock.
Okay.
Because, rock is any natural. Well, a mineral is a naturally occurring crystalline substance. A rock is an aggregate of minerals, and the surface of all but one of the outer moons are ices. I say plural ices. That's water ice, ammonia, methane, carbon dioxide. We expected it to have an icy surface, but that out there is rock. So, and it also had lakes of liquid ethane and methane, which were predicted in advance. So had it splashed down, it would have floated.
Okay.
So yeah, I mean, the surface wasn't a surprise as far as its composition.
Oh, okay. What were the conditions like on Titan? You've already answered part of that. The temperature, atmospheric density, surface gravity, things like that.
So the temperature was about 90 kelvins, which is about 280 below Fahrenheit. So it's nippy. As far as the atmospheric pressure, the pressure at Titan's surface is roughly 1.6 bars, which is slightly more than 1.5 times Earth at sea level. So its atmospheric pressure is actually higher than here. So it's got a thick atmosphere, but Titan is slightly larger than the planet Mercury, but being a large fraction of it being ice, its density is lower, so it's not nearly as massive as Mercury. But what atmosphere a body can hold on to is a combination of its gravity and the temperature, because the temperature dictates how fast molecules are moving. And if you do the calculation for escape velocity from a body's surface is independent of whether or not the object in question leaving is a spacecraft or a molecule. So if it's cold, the molecules don't move fast enough to achieve escape velocity. And so being cold, being at 9.5 times Earth's distance from the sun and being a fairly large body, Titan is like the only moon with an appreciable atmosphere, which is actually thicker than ours. It's mostly nitrogen, like ours, but it also has hazes, a photochemical haze, which gives it that orange appearance. So it looks like a basketball.
This is a bit of a touchy-feely question. How did you feel watching the landing unfold, and what was the mood in the room?
I wasn't in the room during the landing, but it was kind of amazing. We were landing this object on Titan, on a moon of another planet. It was really astounding, and I would even go as far as to say jaw dropping. And one of the first things when you asked that came to my mind is that today, given the environment we have online, you would instantly be just swamped with people saying how fake it was. Take another moon landing, right?
Mm-hmm. Yeah. Okay. Yeah. Good point. What did you anticipate seeing when it landed on Titan, and what did your colleagues expect to see? More to the point, did anyone other than me hope to see trees and shrubs waving their leaves in the breeze at a temperature of 90 degrees above absolute zero?
You know, we were the running joke on our imaging team for that was, you know, imagine we see roving bands of dinosaurs on Titan. You know, that would guarantee a mission extension.
Mhm.
But, you know, we kind of already knew some of what we would find. We, you know, due to an understanding of the kind of elements we find and compounds we find in the outer solar system, plus an understanding of the temperature and pressure at the surface of Titan, we kind of knew that there would be lakes of ethane and methane. We were kind of surprised we didn't land in one. And we were surprised that the how they are partitioned across the surface of Titan. But, you know, as far as seeing the mountains we saw, I think that was a little bit of a surprise. There's some you know, evidence that Titan is still an active body, and we saw that almost, you know, immediately. But as far as, you know, what we saw, I don't know that what we saw was appreciably different than anything anybody imagined. I'll tell you one thing we did see is there was a surface in the surface science package. We had an imager that could take images from in situ, in place, when we were on the surface. And one of the things we saw was that at first blush, you could convince yourself that this is from the surface of Mars. It looked very similar to some of the Mars images. But on the other hand, when you look closely, the rocks in the image were rounded, like river rock, like they'd been tumbled in a stream. So we had an immediate suggestion that there had been flowing liquids here.
Mm-hmm.
So that was one of the things that jumped out at me, was the fact that it looks like we're in a riverbed.
Mm-hmm. I was particularly
I don't think
fascinated
anybody
by it.
expected that, but you know, we kind of knew it was going to be flat, because when you pick a landing site, you often, especially a first landing site, you often pick a place that's comparatively boring, because comparatively boring means safe. And, you know, for this first landing, for getting this down for the first time on a new place, you want to emphasize safe over cool.
Okay.
And it still was both.
Okay. Cassini also did a flyby of Enceladus, in which the probe flew through the outgassing plumes and, using the mass spectrometer, detected carbon dioxide, organic chemicals, and water. Why was the discovery of outgassing plumes of subterranean liquid water such a big deal within the scientific community?
So we have to go back to Voyager. In fact, when Voyager discovered an outer ring, the E ring, there's this large rarefied ring, and I say large in aerial extent. It's actually very, very low density. You know, if you're a Saturn scientist, by the way, your alphabet goes D, C, B, A, F, G, E. That's the order of the rings for inward out. So the E is the outermost ring. It's very wide. It's very low density. It's made mostly of micron-sized ice crystals. Now in space, micron-sized ice crystals go away on short notice, on short order. They sublimate, they sputter, they just don't last. But we have this E-ring as a fixture. So if your individual components don't last, but your structure lasts, that argues for a source. Something is resupplying this ring. And we could see that Enceladus orbited within the most dense part of the ring. It had its own little torus where the E-ring was slightly denser. So instantly, scientists went to Enceladus and said, this is your source. We may have ice volcanism on Enceladus. And we knew it would be ice because the surfaces of all but Io in the outer solar system, all these moons are icy. Like I said, ice is a rock out here. So we said, hey, there could be icy plumes on Enceladus. Let's look for them. And we found them fairly short. We found them by 2005. We'd already seen the plumes. So by the time we flew through them to use our INMS instrument, the ion and neutral mass spectrometer, to actually sample them and get the analysis of what the composition is, you know, we knew that they existed. We knew that we kind of had an idea they were icy. There was some surprise in the amount and variation of organics. Now, As far as there being carbon dioxide, not a surprise. As I said, the ices in the outer solar system, the ices in comets, there's sort of four biggies. There's water ice, ammonia, methane, and carbon dioxide. So that there's carbon dioxide there, not a surprise. Ammonia, not a surprise. Methane, not a surprise. There was some other carbon compounds that maybe were a little surprised.
Okay.
Did I answer your question?
Yes, you did. Were there any follow-up investigations of Enceladus? And if so, what did they learn?
I don't remember how many total flybys we had, but we had a lot of flybys. We had some very close ones. We had some very far ones. We had a couple that if you were standing there, you'd be, ducking as it screamed overhead. Okay. So, and they were for different reasons. Some of them were imaging passes. Some of them as we said, we passed through the plumes. Some of them different kinds of imaging. We found that the vents or the geysers were located in the southern hemisphere in what are called tiger stripes. There's this region that looks like the stripes of a tiger, hence tiger stripes. And we would use different imaging systems. So we had 4 different kind of imagers on the spacecraft. We had my instrument, ISS, the Imaging Science Subsystem, not International Space Station. We had SEERS, it's our infrared. We had UVIS, which is our ultraviolet. And then we had VIMS, which is our multispectral imager, which when it takes an image, or we call it a image, it takes 350 plus wavelength bands simultaneously. We use that for compositional mapping. So we had a lot of different kind of measurements we would make at different resolutions, different distances, meaning different resolutions. And since Cassini, very few of the instruments articulated. They didn't move, they were body fixed. So you point where the spacecraft points you. Each pass would emphasize a different type of instrument. Some would be remote sensing, some would be maybe radar. So just to fully get the understanding of this moon. So we had many passes. We did all sorts of different science at different resolutions to get composition and imaging.
You gave a TEDx talk about the search for life in the solar system. What were some of your observations and what were your conclusions?
I don't remember what the TED talk, that was a long time ago. That was when TEDx talks were in their infancy, and they've changed a lot now. It's more about your personal stories than it was perhaps back then. I kind of like to do another one, but as far as, I don't remember exactly what I said, but what I would say now is, the search for life is about finding water, because everywhere you have liquid water on Earth, you have life. And it doesn't matter where you find it. And it doesn't matter what the temperature is. It doesn't matter what's dissolved in it, salinity, acidity. You find stuff that, as long as there's liquid water, there's life in it, pretty much, with rare exceptions. So our search for life begins with a search for liquid water. And clearly, since we found droplets of liquid water in the geysers of Enceladus, there's evidence for water in the subsurface there. There's evidence for water in the subsurface in Europa. And actually a lot of the outer moons, the larger moons in the outer solar system, like the Galilean satellites, like Titan, have evidence for subsurface oceans, and where there's water, there's life. One of the interesting things is you'll often hear planetary scientists say, we study other planets to learn more about Earth. And that's true because Earth is more complex than these other places. We have an atmosphere and a hydrosphere and a biosphere and a cryosphere. All of these interact. So these things, in all of Earth, it's hard to deconvolve these competing effects. But when we go to other planets, sometimes they're more simple. So we can look at what's an effect of an atmosphere, what's an effect of ice. One of the places where we flip that script is when we find extremophiles on Earth, we're understanding that our search out there can expand because we are finding life wherever there's liquid water. We're starting to think more creatively about where we can find it in the solar system. So when we talk about extraterrestrial life, we're starting to think a lot more that might not be in Zeta Reticuli, it might be on a moon of one of the outer planets. I think that tracks. If it doesn't track with what I said then, it should.
Okay. In 2008, you attended the invitation-only Sci-Fu Unconference at Google headquarters in Mountain View, California. Unless you signed a non-disclosure agreement, what did you see and hear while there?
That was a long time ago. So, but what Google does is they take nominees, and usually it's by previous invitees, and they just invite a bunch of people from different disciplines, ranging from science and philosophy and just get them together, and they start talking, and they do presentations, and hopefully something comes of it. It's an unconference because there's no schedule. You make your schedule while you're there. So it's a weird format. It's a cool format, but when you get a bunch of I'll say supposedly smart people. I don't want to be
Well, I would say it then.
Together and see what they come up with. That's kind of the idea. I would love to go back.
Okay. Did you give a presentation or participate on any panels?
I did. We talked about Cassini and the things that we're discovering there. It was pretty straightforward. Some people were coming up with things that were sort of synergistic between different disciplines. I just said, here's what we're doing with Cassini. Here's the state of what we're discovering in the here and the now. So, okay. I mean, it was cool. It just wasn't anything that grew from that conference.
Oh, okay. Okay. Let's talk about your consultation work for TV and movies. I understand how you would consult for the film Gravity, but Pirates of the Caribbean, Dead Men Tell No Tales, what advice did you give them?
In that film, we have Karina Smith, who is she's thought to be a witch until we find that she was trained to think scientifically. And okay. There's a lot of astronomy in that film. The one thing I was fortunate about is that, in my series of books, the Hollywood Science, I'm currently working on the third book. One of the things we explore is, in going into accuracy in TV and film, is the different roles that writers and directors play in TV and film. And TV tends to be writer-centric, and you're brought up on by an executive producer who's also a writer. But film is director-centric, and oftentimes writers are interchangeable. So your fortune as an advisor might be, and probably is tied to the writer, whoever asked to bring you aboard. And sometimes there's rewrites and rewrites and rewrites, and your advice may not make it to the end game, to the final version. But I was fortunate in that case, and in Gravity for that matter, that on Pirates, Jeff Nathanson was the writer from beginning to end. So in other words, I had a relationship with him. We shared things. In other words, I looked for things that were in the sky, that you could see in the sky in the mid 1700s, that we could use for omens and portents and guideposts for the film. And so I said, hey, here's this cool situation in 1748. Here's this cool thing in 1785. Here's this, and it didn't really have to be, we didn't give a date when this was happening, so, for good reason. But what we did do is we found things that actually did exist and tried to tie those to our story. Okay, cool. So, and one thing's really cool. If you look, there's one poster that you see for that film. It's a gold skull and crossbones. And if you look closely at that, there is a ton of astronomical symbolism in that. There are jewels that are constellations. You'll see that on the crossbones, there are cracks, which if you look closely are equations. You'll see that down the center line of the skull is a comet trail, and there's a crack going the opposite direction that splits into three, and that's a trident. Wow. Okay. Also the symbolism for the film. There all sorts of things are in that one movie poster. Okay. Okay. That covers a lot of my next question. Back to the movie Gravity, is the way I wrote it. In consulting on a movie, what exactly who do you interact with? What's your day-to-day activity? And are you ever on set while they're shooting? Again, TV is different from film, and I generally prefer TV, but in Gravity, it turns out that the film was written by Jonas Cuarón, primarily, who was Alfonso Cuarón's son. And, Alfonso directed it. So those two wrote it, and again, the same writing team from beginning to end, which again, doesn't happen that often in film. So I met with those two. I got connected to them. I met with them in the lobby of Chateau Marmont. It's kind of a ritzy hotel on Sunset in Hollywood.
Mm-hmm.
And we just sat down and we were there for like 3.5 hours just talking about orbits and space debris and the way doors open in the space station and things like that. They had an animation at that time of Dr. Stone like wriggling out of her space suit, which looked sort of like a berth in that sort of cupola window. And they didn't even know who was going to be Dr. Stone at that point in time. In fact, they went through multiple people for both main characters. Mm-hmm. And so, it wasn't Sandra Bullock, but I did see their vision, their mind's eye for what that scene was going to look like. Mm-hmm. So it was cool. And we talked about a lot of things. They told me that their motivation for a lot of how this is going to look was the Hubble repair mission IMAX film. Mm-hmm. So they wanted to capture the grandeur of that film, but also the danger of space, which they felt hadn't been covered in any sort of realistic way, or at least not well. They we watch Star Trek and Stargate. Well, I watch Star Trek and Stargate, but and we get the sort of, I think, sort of deconditioned to accepting how dangerous space is. And they wanted to show that space will kill you. That got some pushback from audience members who thought that he was anti-space, that Mr. Corleone was anti-space and he was trying to scare people. But no, he wasn't. He was just trying to give a realistic view. And I think you see that now in For All Mankind. Mm-hmm. They show how dangerous space and space exploration can be. Mm-hmm. But we got some blowback on that. Mm-hmm. So, but those are the kind of things we discussed. Mm-hmm. One of the things I think that's going to put a damper on space tourism is people don't realize for how much of your first few days you've got your head in a bag, because a lot of people get SAS, space adaptation syndrome. They're throwing up because they're just not used to it. And eventually most people get acclimatized. But that's why we see in the beginning of the film, Sandra Bullock is sick. She's trying not to hurl. And they don't dwell on it, but it's a nice little touch to show that most people up there are having a rough time the first couple of days. Mm-hmm. Mm-hmm. So yeah. Anyway, those are the kind of things we discussed. Mostly the technical aspects of what's going to go down. And I went home later that night, and Warner sent me the script, and so I started going through it with red pen, just changed dialogue and a few things here and there. Mm-hmm. Or I can't say I changed them. I can say I recommended changes. Okay. As a science advisor, you don't change anything. Okay. And I should point out that's a common misconception for science advisors. People sort of, when there's something wrong, they assume that science advisors have almost copyeditor-like say over the science. No, we made recommendations. Okay. But that said, when I got my first gig in the industry on Battlestar, I made the conscious effort to say that I'm never going to throw my production under the bus. If it's wrong, if I didn't do a good enough job of selling why we need to change this, or it just wasn't going to fit in with the story they wanted to tell. Mm-hmm. Okay. So you'll never see me. You'll see some occasionally science advisors say, "Well, I didn't say that. I told them this, and they just didn't listen to me." No, that's not how you get additional work.
That was Dr. Kevin R. Grazier. This has been From Here to the Stars, a video series produced by the Interstellar Research Group. The IRG is a non-profit organization dedicated to thoroughly exploring the science and engineering that can eventually open up the reality of interstellar travel. Find out more about our next symposium at irg.space. I have been your host, Stephen Euin Cobb. If you enjoyed this video, please hit the like button, and you can subscribe to our channel for other such videos. On behalf of all of us here at the Interstellar Research Group, I thank you.